Hello everyone. So let's start solving the next 5 questions of the JAM 2019 organic questions. Right. So the question number 6, the major product formed in the following reaction. So what you see is here is a bicyclic molecule and you have ketone and you have hydroxyl group. Okay. And then what you are using? You are using trifluoroacetic anhydride and H2O2. Whenever you see any acid anhydride in presence of H2O2, remember it will form peroxy acid. Okay, so the first step will be like this: the trifluoroacetic anhydride. Trifluoroacetic anhydride, first you have to understand what is trifluoroacetic acid. So trifluoroacetic acid is CF3 COOH. Okay, COOH. So when two molecules of them come and H2O is lost between them. Okay, and H2O is lost, that is your anhydride CF3. Okay, so just remove H2O and what you get is that is acetic anhydride, sorry, trifluoroacetic anhydride. So this is the compound. Then H2O reacts, H2O2 reacts OH. Basically oxygen with its lone pair it attacks, this goes up, comes down, this leaves, and you get peroxy acid or peracid. So now I think it becomes quite clear. If you have ketonic group and you have peroxy acid, what is the reaction which it will undergo? It will undergo obviously Baeyer-Villiger reaction. Okay, so what happens is, if ketone is there, oxygen gets inserted. Oxygen can get either inserted here, or oxygen can either get inserted here, and it will give you ketone, and it will give you, sorry, ester. From ketone it will give you ester. So the question is, which side it will go, which side the oxygen will insert, which will it insert, this side or will it insert this side? Let's look into it. Yeah, so basically what happens, once this oxygen lone pair goes and attacks here, and then this proton is taken away by this oxygen, so I have shown directly as this step, you get this OH, and then this gives anchiminic acetylene, this comes down, and then a bond will move and attack on this oxygen so that this leaves. So when it is moving, it looks like it is coming with the electron, but actually if you see the intermediate, a three-membered ring will be formed. It has carbocationic character, it has less amount of electrons, so that carbon moves whose carbocation is more stable. So if you see here, if this carbon had moved an attack on this oxygen, this, if you look at the carbocation here, this will be primary carbocation. But if this moves, it is having a tertiary carbocation, because you see here 1, 2 and 3 substituents are there. So tertiary carbocation is more stable. So always migration of more substituted carbon occurs in Baeyer-Villiger oxidation. So this moves in. So if you don't know mechanism also for it's all right during competitive examinations, such competitive examinations, because what you have to look for is, wherever you see more substitution, just insert oxygen in between here, something like this, and you get a ester. And then what happens is, because you see product does not stop here, generally you will be thinking that this product stops here, but this looks quite unstable, and therefore this moves apart, because if it moves you get a stable tertiary carbocation. So this breaks up, takes a proton and becomes carboxylic acid like this, and then when this moves out you get a carbocation here, and then alcoholic part, this goes in and you get this kind of product. So the answer is option number A. Okay, whatever said is written here. So next question, the correct option for the product. So you are having this pyridine, 3-chloropyridine, and you are adding NaNH2 ammonia. So whenever you see NaNH2 ammonia, no, generally on aromatic ring, it will be for nucleophilic substitution reaction via benzyne mechanism. Generally whenever you look at it, no, this is what thought should come to your mind. So here they are asking you to, they want to see that do you have understand about the regioselectivity in this reaction. So now basically what happens is, in benzyne mechanism, a proton on the alpha carbon to carbon containing the leaving group here is Cl, Cl minus leaves, you know that. Okay, So alpha carbon you are having the proton. So this proton will be taken away and you get a triple bond here. Okay. So now alpha to it, two types of protons are there. One is this proton, one will be this proton. If you remove this proton, what happens? You get for some time negative charge here. This negative charge is next to nitrogen. See, negative charge is basically lone pair of electron. Nitrogen also has lone pair. So they face lot of electronic repulsion. So this is unstable. This does not happen. So what happens? What happens is this NH2 minus takes proton from here, and then this leaves, and you get a benzene. So you might think that what happened double bond. See, I have made it look like this just that because it looks beautiful. Does not matter. You could have put here double bond here. That's fine. But this looks beautiful. We don't bother about this because you know it is not localized. It's delocalized. You get here like this benzene. Once benzene is formed, both side NH2 will attack. So this NH2 minus attacks here. This goes and picks up proton from the solvent, that is ammonia. See, otherwise it could have attacked here, and this picks up proton from the solvent, that is ammonia, and therefore you get this product. So what are the products you are getting? You are getting NH2 at position number 3 and NH2 at position number 4. Okay. So the answer should be C. So the answer is C. Okay. So this is the answer. So this goes and picks up proton. This goes and picks up proton. So answer is C. Okay. Moving on to the next question. The increasing order of acidity in the given molecules in aqueous media. In aqueous media, you know, the acid which is present is H plus or H3O plus. That is the better answer. So you have to look, how will you know anything is more acidic or less acidic? Basically, you have to remove the proton. Once you remove the proton, look at the conjugate base which is formed. Anything acid because it gives away its proton, and then you have to look at the conjugate base. Even after giving proton, if the conjugate base which is formed is stable, then it is more acidic because it doesn't mind losing proton, so it loses proton. So here what all things are there? One is phenol, one is ketone, one is acid, carboxylic acid, one alcohol. So very clearly acid will win. Okay. And then comes phenol, and then will come this ketone, and then will come your alcohol. Let us look into reasons. Let us look into reasons. See, what happens is if you remove proton from this, you get O minus. This O minus is stabilized by resonance through this oxygen. This negative charge not localized on this oxygen. If it was localized only on oxygen, it will be unstable. Why? Because oxygen having lot of negative charge will want to go and attack again the proton and take back. But here negative charge comes here, this comes up. So negative charge delocalized between two oxygen atoms, and oxygen is more electronegative than carbon. So it stabilizes negative charge quite a bit. Apart from that, fluorine is there. Fluorine pulls electrons. So see here, through sigma bond it pulls the electron negative charge here. So again negative charge is reduced, is delocalized, fluorine is taken away. So it's making this very stable. So this will be more stable. So this will be strongest acid. If you look at phenol, if you see, it is having more delocalization. If you remove the proton, you get negative charge. This comes here, you get negative on ortho position, then negative on para position, again on ortho position. So like there are only two oxygens in carboxylic acid, only two oxygens were delocalizing, but here one oxygen and 3 carbons are delocalizing. So you may think phenol is more acidic, but that's not the case. Carbon's electronegativity is nowhere comparable to that of oxygen. Even one oxygen will stabilize negative charge much more than these 3 carbon atoms together. So this will be second acetic acid. And then if you look at ketone, so if you remove this proton, you get negative charge that gets delocalized. So negative charge is delocalized between carbon and oxygen. You can see here, so it is stabler than this one because here only oxygen is stabilizing the negative charge. Okay, so the answer should be which is first? So 3 should be most acidic. So 3 is most, all of them are given. Second will be a phenol. So second will be 1. So you are left with either C or D. Then 2. So then 2. So D is your answer. Okay. and D is your answer. Did I write or not? Did I write C? Why did I write C? What is C? 3, 1, then I wrote 4. Okay, so I'm sorry, I have done. Oh, wait. Okay, sorry. See, here what is happening is you are getting negative charge on carbon, whereas here you are getting negative charge on oxygen. I'm so sorry, okay? Here you are getting negative charge on oxygen. Oxygen will any day stabilize negative charge more than carbon. Here one of the chemical structures, but major the negative charge is on oxygen, and therefore methanol is more acidic than your acetone, okay? So sorry, so the answer is option number C. Next question, the compound formed upon subjecting the aliphatic amines to Lasagen's test. So Lasagen's test is very simple. You must have done in your lab. You take a small glass test tube kind of thing, very small test tube. In that you put little sodium, you put your compound, and in the sodium you heat it up, and then you see different colors. Then you know it has nitrogen or not. So basically what happens there, if the molecule is having amine in such a high temperature, when it reacts with sodium, everything breaks open. And then Na reacts with the carbon and nitrogen and forms NaCN. So this is the question which is asking. So the product form is NaCN. What happens later is also interesting. You should just know this NaCN later reacts with ferrous sulfate to give you sodium ferrocyanide, which then further reacts with Fe3 plus to give ferriferrocyanide, which is Prussian blue in color. So once you see this, you know that it is having nitrogen. So here they have asked just about NaCN. The answer is NaCN. Okay. Next question. The compounds formed, compound or compounds, so more than one options are possible, formed as intermediate or intermediates in the following reaction sequence is or are. So there are more than one correct answer possible. Okay. So you are having anisole, and then para position you are having Me. So you know anisole will pump electron more than methyl group. Just you have to remember this part, because it pumps electron by resonance. Resonance electron donation is much more stronger than I effect, inductive effect. So first you are doing is Birch adduction. So sodium liquid ammonia, lithium liquid ammonia, followed by ozonlysis, then NaBH4, then tosyl chloride, then LaLH4. So we have to do for each step and keep seeing what all the intermediates we have. So first step is your Birch adduction. So when you do Birch adduction, you have to look where the pumping group comes. Sorry, where the double bond comes. If you have electron donating group, then double bond comes on the between the atom containing electron donating group and neighboring carbon. Whereas when you have electron withdrawing group, this carbon which has electron withdrawing group does not get double bond. You get double bond here and here on the neighboring carbon atoms. So reduction is happening. The benzene is becoming cyclohexane diene compound. Okay, but if you have electron donating group, you get here next on the carbon atom on which electron donating group is there. Whereas if withdrawing group is there, then on the farther end you get on the alpha beta position double bond. Why is such? What's the reason for such reduced selectivity? The thing is, it goes by radical mechanism. First step is both of them get electron. Now both the electrons, once they separate, they will pick up electron from the lithium. Lithium gives Li plus 1 electron minus, we have seen here. This electron will be picked up. The question is, will this electron pick up or this electron pick up? If this electron picks up, you get negative charge on the ipso carbon, to the electron withdrawing electron donating group. So this is pumping electron, and already negative charge is there. It will make it very unstable. Why? Because it is unstable because of negative charge. You want to make it stable, you have to reduce the negative charge. It is negative charge, you are donating more electron, you are increasing the negative charge, you are making it much more unstable, and therefore electron will be taken from this ortho position so that you get negative charge. And then what happens is this comes here, to get double bond here, and then again See, the two negative charge will try to be as far as possible. So 1 and 4 position the best part. So it takes a electron you get, and they both pick up and you get like this. Whereas when you have withdrawing group, negative charge on ipso carbon will be favored. So you get both electrons here. Electron comes here because negative charge make it unstable. But if it on this will withdraw. It will reduce the negative charge. It will increase the stability, and therefore you get like this, and then you get here. And you see 1 4 position negative charge will be there, and then you get this. So here what we are having, here we have OMe is pumping group, this is pumping group. So very clearly you get negative charge on the, you get double bond on the carbon containing pumping group. So I have shown here like this, you could have shown like this also, but yeah, I have shown like this, both are fine. You get double bond here, not on the alpha beta. You get this is the first intermediate. Then you are doing ozone lysis. Now ozone lysis, ozone acts as an electrophile, very important, okay. Ozone acts as a electrophile, it accepts electron. So which pumps more electron? Will methyl pump more electron or OMe pump more electron? Of course OMe, I just now told some time back, because oxygen pumps electron through plus R effect, whereas methyl will pump electron through plus I effect, and resonance effect is much more stronger. So what happens is it forms ozonoid. You know, this is the ozonoid which forms, and then you put dimethyl sulfide, it comes out as dimethyl sulfoxide. This breaks up, and this breaks up, so you get here, you get ester part. Basically just break the double bond, put oxygen this side also and put oxygen this side also. That's what is happening. So you are breaking it open, and when you put oxygen this side, this becomes ester, this becomes ester, and this becomes aldehyde, and you are getting this part. Then what it does next step is reduction with NaBH4. Now NaBH4 is a mild reducing agent. It does not reduce ester. Sometimes it reduces with very, very slow speed, okay. So it does not reduce ester, it reduces only aldehyde. So once you do this, it will reduce aldehyde into alcohol, and then alcohol attacks octosyl chloride, you get OTS. Then you are reacting with LiLH4. LiLH4 is a powerful reducing agent, very powerful reducing agent, but it is hydride donor. It needs some kind of polarity to attack upon. So it cannot attack alkene, because alkene does not have any polarity, any positive charge is not there. Whereas here you can see when ester is there, you are having positive polarity here, so it will reduce the ester and form alcohol. So this is the product form. So the intermediates are A, P and D. Let us look into them. Options A, B and D. So this was the first one which formed after reduction with this one. Then B we saw after tosylation, that means here, and then D was there when we had done this ozone lysis, right? When we did ozone lysis, we got this. So A, B and D, C was not there, okay. Yeah, so that's it for today. Thank you very much.